All right, so this problem says it's found that when a dilute gas expands, so here's the deal in this business. Whenever they say a dilute gas, what they're saying is the gas behaves ideally. You can assume that it behaves ideally. Dilute gas expands quasi-statically. And what that is saying is it's expanding slowly enough where there's enough time for heat to flow in and all that kind of stuff. So you can in fact stop at an intermediate step, have coffee and all that kind of stuff. So it's everything, each intermediate step is in equilibrium. Okay? So I mean that's what all that means. So we'll always use the ideal gas law. Okay? Quasi-statically from 0.4 to 4 liters, it does 250 joules of work. Assuming that the gas temperature remains constant at 300 degree Kelvin, how many moles of gas are present? Okay. So delta E is equal to Q minus W. So the temperature remains constant, so delta E is 0. Okay. 0 equal to Q minus W. Q equal to W. Okay, so the amount of heat it absorbed was 250 joules. Okay. Oh, so this is an isothermal process. Okay. So the work done, okay, so we didn't need that. The work done was nRT log V final minus V initial. Okay. So N was W over RT log V final minus V initial. Okay, so we didn't need this part. But anyway. So the number of moles is N is the work done is 250 joules. R is 8.314 joules per mole per Kelvin. The temperature is 300 degree Kelvin. Log. Now you don't have to convert the volumes because it's a ratio. 4 divided by 0.5 is 8. Yep. And the joules will cancel, the Kelvin will cancel, and you'll get moles on top. So okay, so 0.05 moles. So this was an isothermal process, and the work done in the isothermal process is given by that. Two monoatomic ideal gases, A and B, at the same temperature are at the same temperature. So temperature is the same. So if the temperature is the same, what does that mean?
They're in thermal equilibrium.
Yeah, and the mass of VA square the average kinetic energy per particle is the same. Okay? So if one is heavier, then that means it's moving slower, but the kinetic energy is the same. Okay? Okay. If 1 gram of gas A has the same internal energy as gas B, what are the ratios of the number of each gas? Okay, internal energy of gas A is the same as internal energy of gas B. That is number of, okay, now I'm going to use, okay, number of gas molecules, no, I'm going to use capital N. Number of gas molecules A times MAVA square. So I'm not going to write the arrows, I mean the average value. But this was equal to that. This is equal to that. So NA equal to NB. So what they have given us is, what is this saying? The number of molecules of A is equal to the number of molecules of B. Okay? Okay, so NA over NB is 1. All right. Now part B, the ratio of the atomic masses, okay, 1 gram of A. So Na times mass A is 1 gram. Nb times mass B is 0.1 gram. But this is equal to that. So what are we saying?
Atomic mass of gas A is 10 times that.
So the mass of A is 10 times heavier than B. So argon and helium. Let's see, argon and helium. When a dilute gas, again, what does a dilute gas means?
Functions as an ideal gas.
Very good. Okay. Expands quasi-statically from 0.5 to 4 liters. It does 250 joules of work, just like last time. Assuming that the gas temperature remains constant at 300 degree Kelvin, what is the, no, this is different. What is the change in internal energy of the gas? Okay. Well, okay, essentially the same problem. Okay. So part A, it's isothermal. Temperature is constant, so change in internal energy is 0. Okay. How much heat does it absorb? Now we'll have to use this, okay. And since this is 0, the amount of heat it absorbs is equal to the work done, which is equal to 250 joules. So it was an isothermal expansion, and the amount of work it did was equal to the amount of heat it absorbed. That's what we're saying. Yeah. Consider the process for steam in a cylinder shown below. Suppose the change in internal energy in this process is 330 kilojoules. Find the heat entering the system. Okay, so here's the final state. You can calculate the work done, which will be the area under the curve. They give you the change in internal energy, find the heat entering the system. Okay, so delta E equal to Q minus W. They've given you this. You can calculate this, which is the area under the curve, and so you can calculate that. Yep. So Q is delta E plus W. Okay, what is W? Let's do W. W is area 1 plus area 2. One half B times height plus base is 12 minus 5, 7 liters. Okay, I'm just going to write 7 liters. And a liter is 10 to the minus 3 meter cube. Again, B is 7 minus 5, 12 minus 5. 7 liters equal to height is, and 1 atmosphere, you want this in pascals, is that many pascals. So height 1 is 30 atmospheres, height 2 is 20 atmospheres. Okay. So this works out to 10 to the, that's 100. So 700 times 20 plus 15, 35 joules. Okay, so 55 kilojoules. Okay, you just have to be careful of all the units, okay? Okay, this problem says 2 moles of a monoatomic ideal gas at 5 megapascals, 5 liter is expanded isothermally until the volume is doubled. Okay, so let's draw that diagram. So there's the initial state, pressure, and we'll megapascals. A megapascal is 10 atmospheres, 10 to the power of 6 pascals. Here's an isothermal expansion. 5 liters, 10 liters. Then it is cooled isochorically. Isochorically is until the pressure is 1 megapascals. Isochoric is volume is held constant. Okay. And so this is 5, this is 1. I mean, I'm not drawing stuff to scale. The temperature drops in this process. The gas is now compressed isothermally until its volume is back. Two megapascals. High heat and ice. Okay, so now you want to find the total work done. Okay. Is the work done positive or negative? So this is a cyclic process. Is the work done positive? The work done during these two processes is 0. The work done during this process is that area. The work done during this process is negative of that. So that minus that, this is a positive work. Had you gone in this process cyclically like that, that would have been negative work. Okay. Okay, so clockwise processes do positive work, counterclockwise processes do negative work. Okay. So find the total work done. The total work done is work done in process 1 minus work done in process 2. Okay. So it's nRT log V final minus V initial for process 1 minus nRT log V final minus V initial for process 2. No, process 3. Well, we know the final volume 10 liters and 5 liters. We know that. Do we know this? Okay, the ideal gas law says PV equal to nRT. So in this, for this process, T was constant, so PV will be constant. So P was 5 megapascals and volume was that. So we know this. Okay. So I'm going to write it down here. So PV equal to nRT. So this means PV log V final minus for process 1 minus PV log V final for process 3. Okay, so for process 1, PV will take PV at this point, and for process 3, we'll take PV at this point. Okay, P is 5 megapascals and V is 5 liters. Okay, so V is 5 liters. 10/5 minus P was 2 megapascals, 5 liters, and log of, what is the final volume for process 3? 5 liters. And then we can flip this and make this positive. Okay. So it's okay, so I'm going to do this 25 times 10 to the 3 plus 10 2 times 5 is 10, 10 times 10 to the minus 10 to the and this will be in joules. So 80.6 kilojoules of work was done in that cyclic process. Yeah. All right, let's do this one first and then we'll come back. This is a short problem. Okay. Pressure and volume measurements of dilute gas undergoing a adiabatic expansion are shown below. What does an adiabatic process mean?
Pressure and volume raised to dm are constant.
Right, and
Heat is not transferred.
heat is not transferred. Q is 0. Okay, so PV to the power gamma is 0. And determine gamma for this gas. So you want to find this. Okay, is constant. Okay, what does that mean? So here is P1, V1. This to the power gamma should equal PV to the power gamma for any other. Okay. So we can pick any 2 points. Let's pick 2 easy points. This one, and we'll pick this one. Okay. So this will be 0.1 and this will be a 0.2. So 20 times 1 to the power gamma equal to 8 times 2 to the power gamma. And we don't need to convert any units because you have the same units on either side. 1 to the power of gamma is 1. So 20 divided by 8 is 2.5 equal to 2 to the power gamma. Log 2.5 equal to gamma log 2. Okay. Okay, so what kind of a gas is this? So here's what we're able to say. The gas is a polyatomic gas. Okay. So just from those numbers, we're able to say this. Okay, let me remind you of something is a quantity is a state function. So here's the pressure and volume. This is the state of a gas. What thermodynamic variables are state functions? So this is the state of a gas, and energy is a state function. Pressure is a state function. Volume is a state function. Anything else? Temperature depends only on the state. Entropy also, and so on. These are state functions. These guys don't care about the history, how you got there. Okay, they just depend on the state. When you go from here to there, the work done depends on the path taken. The heat absorbed depends on the path taken. Change in internal energy does not depend on the path taken. Okay, so here is the first law of thermodynamics. Change in internal energy is, this is path dependent, this is path dependent, but this is not path dependent. So the path dependence cancels out. Yeah. Okay, and that's what we're going to prove in this problem. Consider the process shown below. In the process ABBC, 3,600 joules and 2,400 joules of heat are added to the system respectively. So 3,600 joules and 2,400 joules. Okay. Find the work done in each of the processes AB, BC, AD, and DC. Okay. What is the work done in AB? 0. Work done in BC equal to P times delta V, which is 3 atmospheres times 4 liters.
Wouldn't it be all 5 atmospheres? BC, because the AD would be negative.
Okay. All right. So that's 10 to the 2 and then 20. So 2000 joules. Okay. What is the work done during AD? It's 2 into 10 to the 5 pascals times 4 into 10 to the minus 3 meter cube. 800 joules. Okay. And work done during DC is 0. So if we have the work done for all paths. See, we said that the work done in going from point A to B is path dependent. If you go along this path, the work done is 2000 joules. The work done along this path is only 800 joules. So you see it's path dependent. You added heat here. Okay, now find the internal energy change in processes AB and BC. Okay, AB and BC. Internal energy change for AB is QAB minus WAB equal to 3600 joules minus 0. Okay, so when you went from here to here, the internal energy increased by 3600 joules. How about change in internal energy for BC is Q minus W, which is 2400 joules minus 2000. 400 joules. Okay. Find the internal energy difference between states C and A. So change in internal energy in going from A to C is the change in internal energy in going from here to here plus the change in internal energy there. Okay, change in internal energy in going from here to there is change in from here to there plus there. And that is A to B is 3600 joules. And okay. Find the total heat added in the ADC process. In the ADC process. Okay, so in going along here, the work done is AD plus that, so 800 joules. How much was the energy changed in the ADC process? Internal energy change?
It's the same.
Same as that process, which was 4000 joules. along that path, 4,800 joules of heat was added. Okay. So here we go. The work done along this path is 800 joules. The work done along this path was 2,000 joules. The heat added along this path was 4,800 joules. The heat added along this path was 6,000 joules. Okay. So work and heat are path dependent, and the change in internal energy is no. Okay. So again, so that's what this thing is about. The first law of thermodynamics: path dependent, path dependent, path independent. Okay. So 1 mole of a dilute diatomic gas. It takes a good enough picture to read from there.
Yeah, it does.
Let's see. Wow. All right. Occupies a volume of 10 liters, expands against a constant pressure. So this when it's slowly heated. If the temperature of the gas rises by 10 Kelvin and 400 joules of heat are added in the process, what is the final volume? Okay, so 10 liters expands at 2 atmospheres. Okay, so this is 2 atmospheres. If the temperature of the gas rises by, so delta T is 10 degree Kelvin, and 400 joules of heat are added in the process. Okay, so the work done in this process can be calculated. Work done is, it's a dilute diatomic gas. Work done is P delta V, which is and delta V is okay. It's PV equal to nRT. It's a constant pressure process. So P delta V equal to nR delta T. Delta V equal to nR so work done is P delta V is nR delta T over P. So the P cancels, work done is nR delta T. It's 1 mole, R is 8.314 joules per mole per Kelvin, and delta T is 10 Kelvin. So 83.14 joules of work is done. And then what do they want us to ask when it's like the temperature? What is the final volume? Okay, so now we can go back to this and calculate the final volume. Yeah. So work done is that. So now the work done is also equal to P times V final minus V initial. So 83.14 joules equal to 2 atmospheres, and delta V in liters times 10 to the minus 3 meter cube. All right, well, we'll just say delta V. So V final minus V initial is 0.42 liters. V final is V initial plus 0.42 liters equal to 10.42 liters. Initial volume was 10 liters. Yep. Okay, it's 1:40.